Hello, everyone. Welcome. Today, we are going to be doing our very first day, from our first unit of grade 9 D Stream Math. So, welcome to the class, and I hope you enjoy the course. Okay, with that said, let's get into it. Today's lesson is about linear relations and first differences. Now, let's just review what is a linear relation. Well, a linear relation is any relation where we can use this equation y equals mx plus b, where m is our slope and b is our y-intercept. Okay, so any equation where we can use those is going to fall into the category of a linear equation. So let's go through some examples. This one says, if you ride the drop zone at Paramount's Canada's Wonderland, you will free fall towards the ground at speeds in excess of 100 kilometers per hour or 28 meters per second. The table gives the rider's speed before the brakes are applied. Calculate the first differences for speed, classify the relation as linear or nonlinear, and create a scatter plot of speed versus time. So let's do that. Let's go here and find the first differences. So to find the first differences, we need to subtract 0. We need to do 0, subtract 4.9. Then for the next one, 4.9 minus 9.8, and so on, right? So let's find those first differences here. Okay, so what's 0 minus 4.9? That's negative 4.9. Oh, and in terms of which order you do it in, whether you do 0 minus 4.9 or 4.9 minus 0, it actually doesn't matter as long as you stay consistent. So if we're, starting here and then subtracting this one, that's fine, but then we must start here and subtract this one, the 4.9 again. So we have to go in the same order in order to get this right. I'm actually going to do 4.9 minus 0. I like that a little bit better, and that's going to give us 4.9. What about 9.8 minus 4.9? Let's see, that is also 4.9. Okay, what about 14.7 minus 4.9? Well, that is going to be, minus 9.8 rather. That is also 4.9. Now, what about 19.6 minus 14.7? That's also 4.9. And then our last one, 25 or 24.5 minus 19.6 is also 4.9. So all the first differences are the same. And I have our new rule I'm going to teach everyone that if all first differences are the same, then the equation, or the relation, I should say, the relation is linear. Or in other words, what does that mean exactly? The relation is linear. It means that if we put it on a graph, it would be a line. Now, how do we know that it would be a line? Well, if the first differences are the same, that tells us that the slope is the same, right? And if the slope is the same all throughout a certain relation, then that's an indicator that it must be a line, right? Because if something's a curve and not a line, well, then the slope is different in different places. It sometimes has a steeper slope or a less steep slope than other times. But when we just have a line, what that means is that our slope is consistent throughout, hence y equals mx plus b, as opposed to, well, m is sometimes this number, sometimes that number. No, m is always the same throughout the entire relation in this case. So we've done part A. It said to calculate the first differences for speed, and we calculated that all of them were 4.9. So we did it. B is classify the relation as linear or nonlinear. We already did that. We already said it is linear, and that the reason it's linear is because all the first differences are the same. Now, they don't necessarily have to all be 4.9. They just all have to be the same. So if they were all 3, it would also be linear. If they were all 10, it would also be linear. If they were all -3, same thing, they would be linear. As long as they're all the same in the same table, then the relation is linear. And the last one says to create a scatter plot of speed versus time. So let's do that. Let's see. So speed, let's put time as our x value. And let's put speed as our y value, and let's plot this out. And it should look like a line if we've plotted the points correctly, right? If it doesn't look like a line, then we have some problem, because already before we said that it is a linear relation and that it is a line, basically. And so if it isn't, then we've got a problem, right? So, okay, so let's do that. So here we have up to 2.5, so 0.51. So let's make this 0.5, 1, 1.5, 2, and 2.5. There we go. And then for speeds, for meters per second, the highest is 25. Okay, so 5, 10, 15, 20, 25. Okay, perfect. So 5, 10, 15, 20, and 25 up there. Okay. All right. Yeah, because highest is 24.5. So if 25 is our last number there, we're good. So the dots would go at 0, 0, 0.5, 4.9. So just shy of 5 there. Very, very close to 5. 1 and 9.8. So very close to 10. Let's see, 1.5 and 14.7. So pretty close to 15. And so on, right? And I'm actually just going to grab this tool here and draw a nice straight line. Oh, the straight line needs to go through all the points, not just some of them. Let's make sure it does. Oh, oh. Okay, and then 2 should be 19.6. So yeah, that looks about right, about 19.6 there. And then 24.5 would be 2.5. So that would be just shy of that 25 mark. So there we have it. There it is. So we have now done part C and created that scatter plot. All right, very good. And I guess too, maybe with the scatter plot, we might not have to draw that line, but we also can it. And that's good as well. Okay, let's do 2 more examples here. All right, so the first one has to do with deep sea divers. So here it says, the table shows data collected as divers descend below sea level. Calculate the first differences. Use the first differences to determine if the relationship is linear or nonlinear. Check your solution by graphing. Okay, so let's figure it out. Let's first calculate the first differences. So 4 minus -2 would be -2. -6 minus -4 would be -2 again. -8 minus -6 would really be -8 plus 6, so that's also -2. And last but not least, -10 minus -8 is really -10 plus 8, which is -2. So therefore, the relationship is linear because all the first differences are the same. Now let's draw a graph to check our answer. So over here on our x-axis, we'll do time in minutes. And over here, we'll do depth in meters. I think that's what m is, meters. -2, 4, 6, 8, 10. Let's draw those axes. 1, 2, 3, 4. 1, 2, 3, 4. Awesome. Okay, so after 0 minutes, it's -2. So it starts here. After 1 minute, it goes to -4, then 2 and -6, 3 and -8, 4 and -10, like that. Awesome. Okay, and then let's draw a line through all of it, like that. Very good. There we go. So yes, that does look to me like a line, and so therefore our solution is correct, right? That the number of minutes is directly proportional to the depth, right, in a linear fashion. Okay, let's do another one. This one says hot air balloon. The table shows data collected as a hot air balloon leaves the ground. Calculate the first differences. Use the first difference to determine if the relationship is linear or nonlinear. Check your solution by graphing. Okay, so 2 minus 0 is 2, 6 minus 2 is 4, 12 minus 6 is 6, and 20 minus 12 is 8. So the first differences are not the same, so therefore it is non-linear. And you might be thinking, oh, but if we took the differences of the first differences and got the second differences, it would be the same. And that is true. However, the second differences being the same actually means it's a quadratic, which is not a linear. That said, you don't have to know that at this point. All you need to know is if the first differences are not the same, which they are not, then it's nonlinear, right? So now let's check that solution by graphing. So we have 0, 0. Here we have our time in seconds. And here we have our height in meters. And let's see, we have for time in seconds 1, 2, 3, 4. And for height, we have up to 20. So 5, 10, 15, 20. That works. Awesome. Okay. So we have 0, 0. We have 1, 2. So here's 2.5. So 2 is a little less than 2.5. So we'll put that right there, a little less than 2.5. Okay. Then we have 2, 6. So 6 is a little more than 5. Then we have 3, 12. So 12 is up here. And then we have 4, 20. So clearly, this doesn't really make a line. If I was to connect these dots, this makes a curve, right? This is not a line. And so therefore it makes sense that it's not a linear relation because this clearly, these points don't represent a line. So that shows us in the graphing sense that, that's just another piece of evidence that this hot air ballooning example is nonlinear. Very good. All right, so let's do a few more examples here. I'm not going to complete every question on the homework. I'm going to leave question 2 for you guys to try on your own. But for question 1, I'm going to fully go through and take up the answers to this. Number 1 says Jody is paid $8.50 an hour to work at the zoo. Calculate her pay and record your answers in the pay column. Okay, so it's $8.50 per hour. So if she works 1 hour, she makes $8.50. If she works 2 hours, it would be $8.50 times 2, which is going to be $17. And then if she works 3 hours, that would be $8.50 times 3, which is $25.50. If it was 4, that would be 34. And then if she works 5 hours, she'd make $42.50. So we already might realize that the first differences are going to end up being the same here because what did we do each time? We just every every extra hour she worked, she got paid extra $8.50. It's not as though if she works more hours, they'll give her more per hour at a certain point, at least not in this example. It's just the number of hours you work directly determines your pay because it's an hourly rate. So the first differences for all of these are 8.5, but let's check on that. 17 minus 8.5 is 8.5. 25.5 minus 17 is also 8.5. 34 minus 8.5 is 8.5. 42.5 minus 34 is 8.5. So therefore, this is linear because the first differences are the same. Now in this case, I didn't ask for that yet, but I'm sure it will in just a moment here. Next, it says construct a graph of her pay versus the number of hours she worked. Okay, so number of hours is one, two, three, four, or five, presumably. And then her pay in dollars is up to 42 and a half. Okay, so if we do 10, 20, 30, 40, 50, then we are good. So that's what I'm going to use just for the sake of using um, a relatively easy scale. I never recommend using a scale that is difficult to use. I always recommend using a very simple scale. It'll make your life easier. Okay, very good. So 1 hour would be $8.50 a pay, so a little more than seven and a half of pay, so that's about there. Okay, what about 2 hours? That's going to be $17. So here's 15, 16, 17's about there. Okay, and then of course 0 hours means $0. I'm sure you don't make anything for doing nothing at your job. And then 3 for 25.5. Okay, so there's 25, and 25.5 is a little above that. Okay. Then we have 4 and 34. So 4 hours means she makes $34. Okay. And then 5 hours is $42.50. That's actually right. Oh, no, that's wrong. That's $45. My apologies. That would be right there. I was going to say that dot looks kind of out of place, and that was why I had read it wrong. So there we have it. We have a nice straight line to show that, every hour she works, she makes an extra $8.50. Or every less hour she works, she makes $8.50 less, is another way to look at it. Okay. The next one says, and it says include labels and titles. I did include labels. I didn't include a title. So I'm going to title this graph, what was her name? Jody. Jody's pay. Jody's hours versus pay is what I will label it. Make sure that when you do give your graph a title, that it's a title that makes sense, but not too long, not too short, right? A title that kind of sums up what the graph is about. So if I read your title and I understand that's what your graph is about, that's what your graph is demonstrated to show me, then you've made a good title. If your graph doesn't accurately represent that, then perhaps it's not a very good title. So make sure the graph, that the title accurately tells us what the graph is going to tell us. Okay, C says use the graph to describe the relationship between her pay and the number of hours she works. So it is linear, would be the answer. It is a linear relation. Right? And now we know that for two reasons. We know that because the graph shows a line, right? When the graph shows a line, that means it's linear. But we knew that even before, right? We knew that from the first differences. When the first difference is the same, then it's linear. That's another way we do that. And then it says describe the shape of the graph. So the shape of the graph is a line, right? Linear is describes the relation it is, right? The relationship. It's a linear relationship. Line describes the shape of the graph, or what does the graph look like? Oh, the graph is a line, right? So the graph is a line. Then it says calculate the first differences in the first differences column of the table. Oops, well we already did that. We did that in this first part, but that's all right. So that's already done. And then F says, describe what happens to her pay when the number of hours she works increases by 1 hour. Well, every time she works an extra hour, she gets paid another $8.50. So we could write that she gets paid an extra $8.50 for every hour she works, right? I mean, that's pretty much how it works at any hourly job. Is every additional hour you work, you make an extra whatever your hourly rate is. I guess in today's day and age, I'm sure an hourly rate would be more than $8.50. I would hope, but I think at one point this was the pay that was available at the time. Very good. Okay, so the second one, I leave this one to you. We may take this up next time in kind of at the beginning of day 2, But I'm not going to take it up here because I would like for you to try this one for yourself, and we may take it up next day, possibly. Also, next day, we're going to talk about more properties of linear relationships as well. So we will see you next day for that. But have a good rest of your day, everyone, and I will see you then. Bye, everyone.